In this episode, we will talk about MMaDA, multimodal large diffusion language models. Okay, let's dive right in. We're unpacking a really fascinating piece of AI research today. It's a new model called MMaDA, and it's trying to do something pretty ambitious, basically unifying the understanding and generation of both language and images, all within a single system. Think of this deep dive as your quick path, understanding the core ideas behind this complex new development. The source describes MMaDA at its heart as a unified multimodal foundation model.
Yeah, and what's really interesting here is the context, right? Building models that can handle both text and images. You hear them called multimodal large language models or MLLMs, sometimes vision language models, VLMs. That's been a huge focus in AI research. Traditionally, approaches often combine separate systems, maybe a large language model, an LLM, paired with a separate image generation model, like a diffusion model. They'd work together, sure, but the underlying mechanisms for text and images, they were distinct.
So MMaDA isn't just bolting two things together then, it's different.
Exactly. Its big idea is using a single unified diffusion architecture, one system that works for both text and vision. The explicit goal is to have one fundamental system and training framework handle everything, bridging that gap, between the initial broad pre-training and the later, more specific refinement stages. It's a fundamentally different approach to building these multimodal capabilities.
All right, so our mission today is to really get inside this paper. We'll explore the core technical breakthrough, how they actually built this model through its unique training process, and most importantly, what it can actually do across text, images, and putting them together. Let's get into that technical foundation first. What's the core concept allowing this unification? Why diffusion for both text and images?
Right. At its core, MMaDA uses the principles of diffusion models, but it applies them in a novel way, so it works across modalities. See, instead of predicting the next token sequentially, that's how traditional autoregressive or AR models work. Diffusion models operate differently. They work by progressively cleaning up noise, or in this specific formulation, undoing a masking process. They basically learn to predict the original clean data, could be text tokens, could be image tokens from a corrupted or masked version.
So it's kind of like denoising, but applying to language too, not just pixels.
Precisely. And the key formulation MMaDA uses is called mask token prediction. It's specifically designed as a mask token predictor for both image and text tokens. You give it an input where some parts are masked out, and it predicts all those masked tokens simultaneously. And this is a really big deal because it enables parallel generation, predicting many parts of the output at once. That's a key difference from the step-by-step sequential generation you get with AR models.
Okay, but how do you apply that same mechanism to images? I mean, pixels and words seem so different.
That's the crucial step for unification, yeah. Images get converted into discrete tokens, just like text. The source actually gives specifics, like a 512 by 512 pixel image gets turned into a sequence of 124 discrete tokens. How? Well, they do it by downsampling the image, reducing its resolution, factor of 16 in both directions, and then using something called a codebook. You can think of a codebook as like a vocabulary, but for visual patterns. The model finds the closest pattern in the codebook. This one has 800 and 192 entries for each little section of the downsampled image, and bam, the image becomes a sequence of these visual words or tokens. Once images are represented like this, as discrete tokens, the same mask token prediction mechanism and the same unified cross-entropy loss function that's a standard way to measure prediction accuracy can be applied consistently across both text and image data.
Okay. That clicks for the unified part.
Yeah.
One model architecture, one core mechanism, this mask token prediction, like diffusion denoising, applied to both words and image components once you've tokenized the images into that common format.
Exactly. Architecturally, it simplifies the problem quite a bit.
Building something this unified, though, it sounds incredibly complex. How do you actually train a model like this to handle such diverse tasks?
Oh, it definitely is complex, and the source outlines this carefully designed three-stage training process. It progressively builds up MMaDA's capabilities.
All right, walk us through it. Stage one.
Okay, stage one is foundational pre-training. This stage is all about building the basic capabilities, text understanding, generation, and that initial multimodal alignment, getting text and images to relate. It uses massive data sets like refined web for text and integrates large common image text data sets. Things like ImageNet 1K are in there too for tasks like generating an image based on a class label like cat or dog.
Got it. Building the baseline abilities. What's next? Stage two.
Stage 2 is called mixed long-caught fine-tuning. Now, COAT stands for chain of thought. That's a technique where models essentially show their work, right? Their step-by-step reasoning process before giving the final answer helps improve reasoning. But here, they hit a challenge. Text outputs and image outputs are just very different formats.
Right, like a math problem answer is text, but the result of an image prompt is, well, an image. How do you unify that?
Exactly. So what they proposed was a unified COAT format. It looks like this. Special token reasoning process, special token result to. This same structure gets applied across different tasks. If it's a text task, the result part is text. If it's an image task, the result is that sequence of image tokens we talked about. And the really brilliant part, using this unified format across modalities helps knowledge transfer between them. Training the model to reason step by step for, say, a complex text problem can actually help it generate images that are more factually consistent, because it learns to structure its thought process even when the final output is visual.
Wow, okay, hold on. So they're not just training it to spit out an output, but to build this reasoning process behind it. And that reasoning skill helps it across both text and image tasks. That's really clever.
It is, yeah. This stage specifically targets reasoning-intensive tasks. Think complex math problems, and crucially, world knowledge-aware image generation. That means generating images where factual accuracy, tied to real-world knowledge, is important. And the data for this stage, it's high-quality stuff, often curated or even verified by other advanced models like LMM-R1 and GPT 4.1 to make sure the reasoning steps and results are solid. The fine-tuning itself involves masking out parts of the results section. The model then learns to reconstruct those masked parts using the prompt and the reasoning process as context. It basically forces the model to align its outputs with logical steps.
Okay, so we have the foundation, then this structured reasoning across modalities. What's the final stage of training?
Stage 3 is unified reinforcement learning, which they call UniGRPO. This stage fine-tunes the model even further, especially on complex tasks needing deep knowledge. It uses rewards to guide the model towards better, more desirable outputs.
Reinforcement learning, RL, right? That's often used for fine-tuning language models. Is it straightforward to just apply it to a diffusion model like MMaDA?
Not at all, actually. This was a major technical hurdle they had to overcome. See, traditional RL algorithms for language models often rely on being able to calculate the probability of generating a whole sequence of tokens, one after another. That's relatively easy for AR models that build sequences step by step. You can use the chain rule of probability, but diffusion models are non-autoregressive. They work by removing noise or predicting masks in parallel steps. There's no simple chain rule to calculate the probability of a sequence of tokens in the same way because of all the masking dependencies. It gets messy.
Okay, so RL for diffusion needed a completely new approach then. How did UniGRPO tackle that problem?
Well, at a high level, instead of trying to calculate that full sequence probability directly, UniGRPO finds a clever way to approximate the policy that's basically how the model decides which tokens to predict. It does this by looking at the expected log likelihood for the masked tokens in each denoising step. And critically, it uses a stable, structured masking strategy, specifically uniformly random steps throughout the denoising process, to make this approximation work reliably and stably. This was apparently key to making RL effective for this type of model, improving on earlier attempts that had issues like needing massive compute or just being unstable.
Huh. So they figured out a way to give the model feedback, reward it based on the quality of its outputs, even though it's generating stuff in parallel during that diffusion process.
Exactly. They found a way to measure progress and align the model's behavior with what they wanted in a way that works with the diffusion mechanism. And the rewards themselves are tailored or diversified, as they put it. For textual reasoning tasks, the rewards focus on things like correctness and getting the output format right. But for multimodal tasks and image generation, they add other things into the mix, like CLP score that measures how well the image aligns with the text prompt, using a separate model, and also image reward, which is a model trained to predict human preference for image quality and aesthetics. These different reward signals are all combined to guide the model during this final fine-tuning stage.
That is quite the training pipeline. Foundation, then structured reasoning across modalities, and finally the sophisticated RL fine-tuning tailored for diffusion.
So after all that, how does MMaDA actually perform? What can it do? Does it work?
Yeah, the results are really the payoff here. The source provides evaluation results across the three main areas, and honestly, the performance is pretty impressive. It often sets new benchmarks. Okay, let's start with textual reasoning. How does it handle language tasks?
On standard language benchmarks, MMLU, ARCC, Truthful QA, MMaDA, performs strongly. It's comparable to leading AR models in its size class, models like Llama 3.8b and Quinn 2.7b. But where it really stands out, and this likely comes from that stage 2 Coty training, is on math and logic tasks. Things like GSM-8K and math. Here, it significantly outperforms ELADA 8b, which was the previous diffusion language model baseline they compared against. You can really see that think process, the chain of thought, paying off. The source even includes an example calculation where MMaDA breaks down a math problem step by step to get the right answer.
So it's genuinely doing the math steps, not just pattern matching an answer. That's cool. Okay, what about understanding both text and images together? Multimodal understanding.
Yeah, this is another area where MNL really shines. On benchmarks that evaluate multimodal understanding POP, MME, VQAV2, others, it actually surpasses some powerful existing multimodal models like SHOO and SDXL. The source gives some compelling examples, like solving geometry problem based on an image, or answering visual questions that require understanding spatial relationships, or even simple physics, like how many apples each person gets if you divide them. And what's neat is that MNO often provides not just the answer, but a reasoned explanation of how it got there. Unlike some baselines that might just give a number, or worse, make basic visual errors.
Okay, so text reasoning is strong, multimodal understanding is strong. What about the classic diffusion task? Text-to-image generation, how does it stack up there?
This is maybe where MMaDA is most impressive, partly because it brings its other strengths, like reasoning, into the image generation process. It excels here. It outperforms well-known models like SDXL and Janus on key metrics. It gets the highest LIP score in their comparisons, which means excellent alignment between the image and the text prompt. And it also gets the highest image reward score, suggesting humans tend to prefer the images it generates. But what's particularly notable, I think, is its performance on the WISE cultural benchmark. This benchmark specifically tests the model's ability to generate images that require real-world knowledge or depict abstract cultural concepts. MMaDA does exceptionally well here, and the source directly links the success back to that joint training on text-based reasoning. It's not just creating pretty pictures, it's creating pictures that are factually consistent and conceptually relevant, even for nuanced prompts. The examples they provide in the paper are great, like comparing Arctic carnivores visually side by side, trying to depict Russian spirit, or showing complex scenes like a cat shopping or detailed cityscapes of Istanbul or Paris. They really showcase both its visual quality and its ability to incorporate knowledge.
It definitely sounds like training all these capabilities together in one model creates a kind of powerful synergy, doesn't it?
Absolutely. The source emphasizes this point quite a bit, and they even show it graphically in their results, Figure 6. They found that jointly training MMaDA on this diverse set of tasks, text, multimodal, image generation, leads to improvements across all of them. So, better textual reasoning contributes to more accurate, knowledge-aware image generation. Improved multimodal understanding helps with both visual Q&A and generating complex visual scenes. It really seems to be a positive feedback loop within this single unified model.
Beyond just the performance numbers, though, are there practical advantages,
Mhm.
benefits to using this diffusion approach for a model handling multiple modalities compared to standard AR models?
Yes, definitely. The source highlights two key practical benefits that are directly tied to the diffusion architecture and how it's trained.
Okay, tell us about them.
First up is sampling efficiency. Because diffusion allows for that parallel generation during its denoising steps, you don't need to generate tokens one by one sequentially, like an AR model. This means you can often get good quality outputs in significantly fewer steps than the total number of tokens in the output. The source shows this quite clearly in their results, Table 6. For image generation, MMaDA gets strong results with just 15 or maybe 50 denoising steps. That's a tiny fraction of the 1024 steps that actually represent the full image resolution. And text and multimodal outputs also benefit, working well with fewer steps. What this means in practice is potentially much faster generation times, especially compared to generating very long text sequences or high-resolution images token by token.
Faster results is always a big plus in AI. Makes sense. What's the second advantage?
The other key advantage they point out is inherent task extension, specifically things like in-painting and extrapolation, because the model's fundamental training involves predicting masked tokens, basically, filling in missing information. It naturally learns the ability to complete partial inputs. It's baked into its core function. Now, previous diffusion models like SHOO had shown this for image and painting, but MMaDA extends this capability across all modalities, text, multimodal reasoning, images, without needing any extra fine-tuning for these specific tasks. The examples they show in Figure 7 really illustrate this well. It can fill in missing words or phrases in a text passage. It can complete a partially masked answer in a visual question answering task using the image context. And yes, it can do standard image inpainting, filling in missing parts of a photo based on what's around it. It demonstrates this remarkable flexibility and generalization that just emerges from its core training mechanism.
That's genuinely impressive, that kind of flexibility built right into the architecture.
Yeah.
So MMaDA really seems like a significant step. It's a unified diffusion model that isn't just a theoretical concept anymore. It performs strongly across a diverse set of tasks, brings new capabilities like sophisticated reasoning into a diffusion architecture. It's trained with novel methods like that unified COT and UniGRPO for RL, and it offers real practical advantages like potentially faster generation and this inherent ability for in-painting and extrapolation across both text and images.
Yeah, it really pushes the boundary of what a single foundation model can be. You've got complex problem solving, understanding text and visuals together, and generating high-quality, knowledge-aware images, all within one coherent system built on diffusion principles.
And maybe that leaves us with a final thought for you, our listener, to consider. MMaDA shows that a single unified architecture and training framework can tackle an incredibly broad spectrum of AI challenges, from very logical reasoning tasks to highly creative image generation. Really makes you wonder, doesn't it? How far can this unification go? What other modalities, maybe audio, video, perhaps even more complex data types, could future diffusion foundation models learn to understand and generate together? And what entirely new capabilities might that kind of deep integration unlock for AI down the road? Something to think about.